All right, welcome everybody to our last webinar from the Fall Technical Conference webinar series. If you've been with us before, if you have any questions, feel free to use the Q&A box and we will get to your questions at the end of today's talk. All right, if you haven't been with us before, the Fall Technical Conference, it's an annual conference sponsored by the American Society for Quality and the American Statistical Association, with two organizations within those. And the goal of the conference is to engage researchers and practitioners in a dialogue that will lead to more effective use of statistics to improve quality and foster innovation. And you can find all the details about the Fall Technical Conference at the website shown here. And definitely save the date for the next conference. We will finally be back in person, fingers crossed, in October 2022 in Park City, Utah. And the theme is mining for quality with statistics and data science. And of course, it's not too early to be thinking about abstracts if you want to present and share your work at FTC next year. So abstracts are now being accepted online, and you can do that at the link shown here on the website. On the slide, I should say, and one presenter for each talk will receive a 50% discount on conference registration. So don't hesitate and get those abstracts in while you're thinking about it. This is our last talk of the webinar series. So if you've been to any of the ones before, thank you so much, and thanks for being here today. All of the recordings for all the talks, including today's, are going to be posted on the website. Actually, the first 8 are already there, along with the slides from each presentation. So if you missed any, or you want to go back and see another one again, visit the website. They're all there. Well, let's get into today's talk to give our speaker the maximum amount of time. So I am the past chair for the Chemical and Process Industries Division. And so it's my honor to announce that this year's award for the Wilcoxon Prize, and this award is awarded annually for the best practical application paper appearing in the 2020 issues of Technometrics. And so the primary criteria are, of course, the value of the application to practical problems, organization and clarity, documented examples, and originality. And of course, it also needs to be readable and solving an actual problem. So thanks to the award committee for selecting this year's winner. And this year's winners go to Tony Pourmohamad and Herbert Lee for their paper, The Statistical Filter Approach to Constrained Optimization. This paper can be found in issue 3 of volume 62 from 2020 and should be made available online for a couple of months. So if you want to go read that paper, definitely encourage that. So first, congratulations to our winners. And representing the two authors is Dr. Tony Pourmohamad. So I'll just do a quick introduction and then kick it off to you. Tony Pourmohamad is a principal statistical scientist in the Department of Biostatistics at Genentech. Prior to joining Genentech, he received his PhD from the Department of Statistics and Applied Mathematics at the University of California, Santa Cruz, where his research focused on constrained optimization for computer experiments. Nowadays, he spends most of his time at the intersection of clinical and non-clinical statistics at Genentech. So with that, Tony, I say again, congratulations, round of applause for your paper, and I'll kick it off to you.
Thank you. Thanks for the warm introduction. So let me share my screen. Full screen and reshare. Actually, can you see my screen in full screen mode?
Yes, perfect.
Okay, and can you actually see my cursor?
Yes.
Okay, perfect. So yeah, thanks again for the warm introduction and for the opportunity to present to you guys. So today I'm going to talk about the paper that won the award, and I'm going to try to highlight some of the results. But what I really am hoping that everybody gets out of this is just the finer details of the method, things that we couldn't include in the paper just because of length requirements and stuff like that. So I hope you get a better idea of what the method is really doing. And so, like it was said, this is the winner of the award. Some information here if you want to go check it out if you haven't already read it. a little bit of a shameless plug. I just wrote this paper also with my advisor. So Herbie Lee was my former PhD advisor. And so the first paper that we wrote on the statistical filter was part of my PhD dissertation. This paper was a follow-up, and I actually want to plug this paper because I actually think it's a much cooler and better idea in a sense. So if you like the first paper, please check out this paper. They're not related in the sense of the methodology, but they're solving the same type of problem. So I assume if you're here for this talk, you might be interested in optimization type problems. And one more shameless plug, me and Herbie just actually wrote a book on the entire topic of Bayesian optimization, which is going to be part of the talk today. So if you're also interested in this, there's a book in Springer. There's a lot of code in there for running the examples and how to actually do this in practice. So check it out if you're interested. All right, so I'll start off with some motivation for the problem and the type of thing that we're trying to solve here. And so if you're unfamiliar with the paper or just the area in general, we're going to be motivating this problem from the point of view of computer models. And so what computer models are physical programs, or they're computer code, basically, so a computer program that represents some sort of physical process that's under study. Typically, the process that you want to study with a computer model, the reason you have a computer model to study it is because that physical process is just not feasible to actually run an experiment on. You could think of an example of like dropping a bomb. You could go out, drop the bomb, make a recording to see what happens when you drop a bomb, but you probably don't want to do it. It's dangerous, it's costly, there are implications that you cannot do this experiment, ethically. And so you build a computer model that represents that physical process that you're going to use to learn about the experiment that you wish you could run, in a sense. Today, the talk is going to be on a type of computer model known as a black box computer model. So we think of it as a black box system in that all you have here are inputs that you can input to the computer model. So the computer model is this black box. So for any input, I'm going to get back out an output, right? So, you have some sort of inputs, you run your computer code, and you get back out what happened. The evaluations of this black box system are going to be expensive. And what I mean by that is for any given input, it could take on order of seconds to minutes to hours or even days to get out a single output. We're going to be in the situation here where we're modeling running our computer code is going to return multiple outputs. So we have at least 2 outputs or more. And part of the thing that we did in this paper was we decided that, maybe there's this relationship between the outputs that are coming out. So typically what you'll find in the literature is that people attack this problem thinking of the outputs as being independent of each other. And so we asked this question in the paper of, what happens if these outputs are actually correlated, and can we model these correlated outputs in some way? Here's a better example maybe to kind of orient you to the problem. So there's this problem that we've solved several times in a few of our papers, and it's been solved by others. It's called the Lockwood problem. And so there's this area in Montana known as the Lockwood area, where there are 2 plumes of contaminants in the soil. So there's this plume A and this plume B. And these contaminants that are in the soil are slowly leaking towards the Yellowstone River. And so the Yellowstone River is a source of water for the community. And so they really are, concerned about making sure that none of the contaminants actually leak into the river. And so what the environmental scientists are able to do is they're able to install a series of pumps. So this A1 and A2, B1 through B4 are a series of pumps that they can install in the contaminated areas. And these pumps can be turned on. They'll suck out the contaminants, go through a series of steps, and then re-inject the contaminant or the non-contaminated water now back into the soil. And so this is a physical experiment that you might not want to run in practice right away, because the inputs if you think about this as a computer model, you could think of this as your inputs to the computer model are these pumps, and the things that you're able to actually change are the pumping rates at which you run these pumps at. Okay, so those are the inputs. And the output here is whether or not you're allowing contaminants to flow into this river. Okay, and so you could go out and do this physical experiment, and you could set these pumping rates to be whatever, and you could observe what happens. But a lot of times you'd be getting it wrong, and you'd be allowing contaminants to flow in. So what scientists actually end up doing is they build a computer model representing this physical process so we can learn about what are potentially the optimal pumping rates so that no contaminants leak in. So to kind of put this into a schematic here, you have pumping rates as your inputs to your computer model. So your computer model is this black box system that represents that physical process. And two of the outputs that actually come out of this computer model is cost, because there's a cost associated with running those pumps. If you crank up the amount of pressure in the pumps, so you're running them at like full pressure, so you're making sure no contaminants ever leak in, you're also running them all the time and you're wasting money potentially, because maybe you don't need to crank up the pumps all the way. Maybe there's a lower setting you could set to and save some money. You also get a contamination status, which is a continuous variable in our case, but it's basically, did you allow stuff to go into the river or not? And so you could think of this as a constrained optimization problem here, because, subject to a given pumping rate, you want to minimize the cost at which you're running the pumps while also satisfying this constraint that you're never contaminating the Yellowstone River. And so recasting this, as what I just said as an optimization problem here, right? We could think of this as, you want to minimize some objective function f of x subject to meeting some sort of constraints that we're going to say are going to be less than or equal to 0. And so in our context, the objective function, we get this as an output of running our computer model, as same as our constraints. So for any input x to the computer model, we get out an f and a constraint value c. And so some of the common problems that you run into in this area are, well, you need to be able to model f and c cheaply. This goes back to this idea that, you have this black box system that you're going to be trying to model. So I haven't really talked about that yet, but you're going to have an underlying statistical model for the black box system. And evaluations of f and c are expensive. For every input we put in, we get an expensive evaluation out. And so we're going to want models that can model these things very efficiently, because running the actual computer model is expensive. We need a model that's going to be able to handle correlation between the outputs of the computer model. So there might be correlation between your objective function and your constraint functions, and we want to be able to model that. And we're going to need an efficient optimization algorithm, again, because of this whole expensive nature. And the other thing I didn't mention is actually we're in the context of derivative-free optimization. And so we're going to have a system that doesn't give us any derivative information. So we can't leverage, a lot of classical methods that are based on optimizing things using derivatives. And so the solutions that we propose in the paper is, well, we build a multivariate Gaussian process to model f and c. And I'll talk about that in a little bit, why we chose that model. We're going to use sequential Monte Carlo methods to speed up our computations. Again, we want a method that works fast, because every time we evaluate the actual computer model to get data, it's going to be an expensive endeavor. So we want something that also runs fast, so that our method isn't the bottleneck. It's really the computer model that is the bottleneck. And we're going to combine filter methods with statistical modeling to leverage optimal properties of both. And I'll talk about that a little bit later. So I'm going to start off with talking about the surrogate model, and that's just another name for a model that represents, so a statistical model that is modeling the computer model. It's kind of a funny concept, right? You have a model, a computer model that represents the physical process, and now you're building a statistical surrogate model that models the model of the model. And so, probably most of you are familiar with this, but I'm going to go through the model that we use. It's called the Gaussian process. There's, the actual real definition here, but all this is saying, and all that you should be worried about here is that, well, if you have some finite collection of normal random variables that have some mean function and covariance function, you basically can write that as a Gaussian process. Why do we use Gaussian processes? Well, if you open up any book or look at any article on computer modeling, they're the canonical choice for modeling of computer experiments. They've been used extensively in this field, and so we also made use of them. They have very nice properties as well. They're much cheaper and faster to evaluate than actual computer model code. So once you've built this statistical surrogate model, you can use your model to make predictions of what you think the actual computer model will do, and you can do it very fast. And probably the nicest property of them, in my opinion, is that they allow for uncertainty quantification at inputs that you haven't tried yet. Okay, so if you think about this as a, you have a series of inputs that you input to your computer model and you get out outputs, right? So the inputs and outputs are your data. You only have data at where you've tried inputs. And so the Gaussian process allows for prediction at the places that you haven't predicted yet. So this, in this notation here, you have, X star being inputs you haven't tried. X is data that or inputs that you have seen. And so your prediction, conditional on the data that you already have, is actually another Gaussian process with these very easy to compute equations for the mean and the covariance function, which if you stare at it long enough, you realize it's a conditional normal equations that you probably learned about in some, intro to probability type course. So very, very easy to use Gaussian processes. Here's a picture just to give you an idea of what a Gaussian process looks like. So in each one of these pictures, you have these little crosses which represent data. And the data in each picture is in the exact same location. And so there are parameters inside the Gaussian process that govern what prediction under the Gaussian process will look like. And so what I was hoping that you'll get out of this picture here is that, you see that you can capture lots of different types of trends using a Gaussian process with the same data, right? So for different parameters of L in this Gaussian process, you can get something that's very smooth with reasonable looking uncertainty bands. You can get something that, wiggles a lot and it interpolates, it's going directly through the actual data that you observe, or you can get something that's really, really smoothing out your data and your process. So they're very flexible models as well. We actually, in the paper, use a multivariate Gaussian process. So there's an extension of, so what I was showing you there was if you were to just fit a Gaussian process to one output, so say like the objective function. Here we want to fit a multivariate Gaussian process because that'll allow us to link. So you would, in a sense, you would fit a Gaussian process for your objective function, a Gaussian process for your constraint functions, and then you would try to link the two using the multivariate Gaussian process. So that allows you to actually model the correlation between these outputs. I don't want to go into it because it is a very complicated model. But I'm citing, this paper that we wrote on the topic prior to the statistical filter paper. And if you're interested in seeing the actual details of that model, you can check it out. But basically, that model allowed us to model correlated outputs from a computer model. And we have this whole fast sequential Monte Carlo inference to be used in that method. When I think about this now, at the time, part of this was part of my thesis for my PhD. And so, this was something that was very complicated, very novel in a sense. And so I think it made a lot of sense. If I would go back now and redo all of this, I probably wouldn't fit this multivariate thing because even though you'll see that you gain efficiencies, I think it's a really hard model to fit. And I think there's a lot of work involved and there's kind of, I don't think the computational overhead of fitting this thing is worth the reward that you get in the end. I think, independent Gaussian process models probably work just as well in some sense, and they're much easier to fit. So that's the statistical surrogate model that we're going to be using. So I'm going to talk about now the actual statistical filter method that we ended up developing. And so before I can jump into that, there's an area that is becoming much more popular in this optimization type of framework where you take a mathematical optimization algorithm. So you take something, like this filter method is actually out of the mathematical programming literature. It's nothing statistical about it. It's almost like, in a sense, like, if you took Newton-Raphson or your favorite optimization algorithm from the mathematical community. And what you end up doing is you hybridize that algorithm using statistical models. The reason being is that there's lots of solvers in the mathematical community that have been developed that have very nice properties. So there's provable local convergence properties, lots of open source softwares. They're very well understood. They're very quick. They're very efficient. But they don't do so well when, they usually are all local. So they're finding local minimums, let's say, in the constraint or in the optimization case. Statistical models are very good at finding global answers, but they're not so great at being fast. They tend to overexplore the space. And, they do excel when, say, your simulation is expensive, noisy, non-convex. And so they're kind of these two pieces, one has very nice global properties, one has very nice local properties. And so you end up marrying the two and kind of trying to take benefits of both. And so this is what we ended up doing in the paper. We took the filter method, which is a mathematical programming method, and then we used, our Gaussian process surrogate modeling, combined the two to come up with an efficient optimization algorithm. So I'll tell you a little bit about filter methods, and then I'll tell you how we actually combine statistical modeling with it. They were introduced by Fletcher and Laffer in 2002 to solve nonlinear programming problems. A filter is like a Pareto front. So if you're familiar with the idea of a Pareto front in multi-objective optimization, it'll simplify, the next explanation I'm going to give. But basically, what you end up doing with the filter method is you define this function h of x, which is going to replace your constraint function in your constrained optimization problem, right? So we were minimizing our objective function subject to a bunch of constraints. And here we're writing h of x as being equal to the maximum of either 0 in each individual constraint. So if this thing is all 0, we've satisfied our constraint. If this thing is any number that's positive, then we've violated the constraint by some amount in some direction. Okay. And the filter, it's going to be defined as the set of all points such that these criteria here are met. And I'll show you what this criteria here means in a second visually. It'll be a lot easier to understand. So again, we're reformulating the problem such that, we're minimizing our objective function subject to now satisfying this new equality constraint that h of x is equal to 0. So what the filter is visually, so you can imagine now you have your black box model, you run a handful of inputs. So here, let's say, I think I have 8 points here. So each point represents one input to the black box model. You run that and you get out 8 outputs. So this is like your initial data that you've collected, okay? And so now you want to construct a filter. And so you've evaluated those inputs. And so you have values of the objective function at the inputs, and you have values of your h function at the inputs. And so the filter is defined as the set of all non-dominated inputs, if we're using the terminology of Pareto fronts. And what that means, I showed you, these equations here. So this fx prime less than or equal to f and hx prime less than or equal to h. But really what's this saying is, if you start from the left-hand side and you think about it as, okay, I have this point here. Is there any point that has a lower f of x value and h of x value? If there is a point that has a lower f of x and h of x value, then this point here is not part of my filter. And you go across and you decide which ones, meet that criteria. They do not get included in the filter, and the ones that don't, then they do get included. So it should be intuitive, I think, that these green points define the filter set, because no point dominates these points. These points here, the black ones, are all dominated by these green points. I'm going to color them red for now, so you know that red means you're dominated, green are non-dominated points. And if you think about this filter, so these green points define a blue region such that anything within the blue region is dominated and is not part of the filter. So the green points are the points that are part of my filter. Okay, so we've now defined the filter. And so if you think about this as just, running an optimization algorithm, no statistical part here yet, you would now try another input. You would get out an output for f and an output for h. And so as you can see, this point just appeared. Imagine I just ran an input and I got a point that lands here in this space. And so it's in the blue area, so it's dominated, and so it's not part of the filter. I run another input, I get this point right here, this green one. It is not dominated by any other point, okay? And so it becomes part of the filter. And so now my filter has filled in this area. And so basically, visually here, any point that falls in the white is going to be added to my filter. Everything that falls into the blue is going to be excluded from the filter. And so you would iteratively run this process trying to find points that fall into the white area. And so, it would continue, the filter would get updated. So you could also see, a point that, is part of the filter originally, you get an input that, it lowers the F value, lowers the H value, and it becomes a new one. And this point becomes dominated and is no longer part of the filter. And this continues basically for your entire budget, right? And so at the end of the day, you've now found a handful of points. So you have these 2 points that satisfy the constraint because H is equal to 0. And you now have a value of F of X that is the minimum. So this value here at say 1.8 is, the minimum value that I found for my objective function subject to satisfying the constraints. So that's the idea of the filter. And so if you think about this algorithmically, you're going to initialize your filter, which I'm calling here script F, based on, running a handful of inputs through the computer model, getting back out outputs. That's my initial filter. And, again, this is an iterative algorithm. So you're just looping here. So while you're not, you haven't terminated, so you haven't used up your budget for points, you're going to obtain a candidate point X star, and you're going to evaluate it. So this is, some point that you think might be the next point for minimizing your function and satisfying the constraint. Once you've chosen it, you evaluate your objective function and your constraint function. And then you say, well, is it acceptable to the filter? If it ended up in that blue area, once you've evaluated it, it's not acceptable to the future, so you don't use it. If it falls in the white area, then you add it to the filter, and then you end up removing any points that are dominated by it, okay? It's iterative, you run it for budget, and you basically keep going, and then you check for termination. There's a handful of extra conditions that were introduced to, so this filter method, it's provably convergent. And so one of the extra pieces of information that gets used is, Fletcher and Laffer, they define this thing that's called an envelope. So there's an extra set of conditions. I'll show what that looks like visually in a second. And you can place an upper bound U on the acceptable constraint violation. So visually, this dashed line here, this red dashed line, is what is called the envelope. And so in practice, what ends up actually getting done is, rather than just finding points that fall to the left of the blue area into this white area, you also need them to be far enough away from the blue area, so outside of this envelope. So this envelope kind of shrinks and expands during the whole process. And so you need the points to be to the left of the envelope to actually be accepted as being part of the filter. And you can define a value U, which is the maximum accepted value for the constraint violation, right? So if I, say I said, 6.5 was too high for my constraint violation, then any point that, even if it falls down here, below this blue part, if this was white, it would not be accepted to the filter just because the violation is too high. So you should be able to also exclude points just based on, what you think is too much of a violation as well. So that's kind of just an efficiency that you add into the algorithm. I've kind of touched on this a little bit, but this is one of the things conceptually that you have to think about as well. There's 3 spaces that you're dealing with when you are working with this filter algorithm. You have a design space, which is the space where your inputs live, right? So here I've labeled all of the inputs. These are the 8 inputs, right? So you have, let's say if this was a 2-dimensional problem where you have 2 inputs to your computer model, so you have an X1 and an X2, you have this 2-dimensional space, which you have to choose inputs from, right? And so you have to also think about how are you selecting those inputs. And so, this is a design space under a Latin hypercube design. You can think of, using that. Once you have those inputs, you pass them to your computer model, and you have what we're calling the constraint space here, which is where do those points live in this F of C space, okay? So this space is important for us because this is where we're actually going to be modeling our data using our Gaussian process. So we actually fit our Gaussian process in the constraint space. And then once we have our Gaussian process and we make predictions of what we think the computer model would do at inputs that we haven't tried, they're going to get mapped into what we call the filter space. So the filter space is taking this constraint space and mapping it such that rather than using C on this axis, now we're using H of X. So everything that satisfies the constraint gets mapped to 0. Everything that has some positive constraint violation, is larger than 0. So all the points that live below 0 here in this picture get mapped to the 0 in the H space. So inputs live in the design space where we have to figure out what we're going to pick. Constraint space is for where we do our statistical modeling. And then filter space is where we actually do the filter calculations to actually run the optimization algorithm. The statistical filter method, like I said earlier, there's this growing nature or field in optimization where we're taking mathematical programmings and we're combining them with statistical models and using both the desirable properties of the two. And so what we ended up doing in this paper was we combined filter methods with Gaussian process modeling. And if you go back to this picture here, this part, actually constructing the filter and running this is really simple. The hardest part here is how do you choose the next input that you want to evaluate to see if you've now found a lower objective function and you've satisfied the constraint. That's really the crux of the problem, is identifying the inputs that are going to maximize your problem while never, failing to satisfy the constraint. And so you have to come up with some sort of criteria. I mean, you could just randomly choose inputs, but you would be wasting a lot of time. So you have to come up with some sort of criteria, because again, also we can't just run every input anyway, because the black box computer model that we have, it's very expensive to run anyway. So we need an efficient algorithm for choosing what's the next candidate point to select. And so that's really the novelty in the paper is, well, we said, well, we could choose the next candidate point as the one that maximizes the probability that it will be acceptable to the filter. And so we just wrote it here as, you're maximizing this probability that your new input X, okay, once you've evaluated H and F of X, is going to be acceptable to the filter. Visually, there's two representations here, but basically you could think of it like this. Let's assume I have this filter, so these green points that define this blue region. I have my envelope and I have my upper bound U. And now I want to decide, so we're just looking at the left panel for now. I want to decide between an input A and an input B, which one is going to be the better candidate point to actually evaluate through my computer model. And so here we have to come up with some sort of criteria to judge which is better. And so we are modeling our data using a Gaussian process. And we're using a multivariate Gaussian process, but even if we weren't using a multivariate Gaussian process, this would still hold. And so what we end up getting is our Gaussian process is really just a normal distribution. And so we can do predictions using it. And because it's a normal distribution, we can make predictions. So we can predict where B and A will fall in here. And then we can have some sort of probability ellipse around those points. Again, because they're normal distributions, these things are nice and easy to calculate. It's just an ellipsoid that you can easily calculate this area of. But the point here is we're using those normal distributions to come up with some sort of uncertainty ellipse. And we're using our probability calculation as follows. We say, okay, you predict point B to be here, point A to be here, and then I'll calculate the amount of area of this ellipse that falls outside of the filter or past this envelope. And so the proportion of this area is compared to the amount of area in this ellipse, and the one that has the greatest proportion of area outside is calculated as being the one with the highest probability. And so I'm going to choose the point that falls with most area outside of the filter. The reason I'm showing two pictures here is because if you were to use the multivariate Gaussian process, you would actually get ellipses when things are correlated that are not axis aligned. So, you actually have covariance basically you have these covariance values or correlation values, and they create these ellipses that are tilted. If you were to just fit an independent Gaussian process for the objective function and an independent Gaussian process for the constraint functions, you would get ellipses that become axis aligned. It doesn't, either way it works, but you can see you get slightly different nature, right? In this picture here, this guy has some proportion of his area that's inside the filter, and had you used a multivariate Gaussian process, this is all completely made up, obviously, but this one would actually be completely excluded And so the, the decision to choose A is a little bit easier here, whereas this one, you'd actually have to calculate this and figure out which one has the higher amount outside. But so the idea here is very simple, right? We're collecting initial data. We fit our statistical surrogate model, our Gaussian process. We do predictions in this space, and we try to figure out which one of our predicted points has the highest probability of falling outside of the filter. Once we have that value, once we have that point chosen, then we would say, okay, let's say A has the highest amount outside. We then run A through the input A through the computer model, and we get out the output. And then that point gets added to the actual data here. And this thing just iterates. So to try to summarize that maybe a little bit better, right? We sample initial inputs from a Latin hypercube design. That's the way we did it in the paper. We initialize our filter with these from this initial inputs. We're going to iterate just like the original algorithm, but here we're going to fit a surrogate model for f and c of x. This is our joint or multivariate Gaussian process. Again, you have to think about the spaces. So then we map our surrogate model in the constraint space to the filter space. So we do all of our prediction in constraint space, and then we map them to filter space. We're going to obtain candidate points x star that maximize the probability of being acceptable to the filter. So, in this picture, we choose A. It's the one that's the candidate point that we think is the next best promising point. You evaluate that point. And then if it's acceptable to the filter, you add it. So it becomes one of those green points in my picture. And if it does, then you remove any points that are dominated. So which points, become blue, the area gets blue, and you have now red points. And you check for termination. Termination here is, you've exhausted your budget, you've ran it sufficiently long. And if you haven't terminated, then, you sample more candidate inputs from a Latin hypercube design to do prediction at using your Gaussian process, and you iterate. Here's an example. This example was not in the paper, but I hope it helps elucidate some of the properties here. So imagine you have this blue curve, which is your objective function, and you have this red curve, which represents your constraint function. Typically, this is a problem that occurs very often in constrained optimization type problems, is that the global minimum ends up being on the constraint boundary. This is not an issue here in the paper, but it's something worth exploring in follow-up type of papers that we've looked at. And so what you end up having here in this example is you have two local minimums. So these orange points represent local minimums, and you have this green point, which is the global minimum. Again, mathematical programs such as the filter method are very good at identifying local minimums. So if you start close to this thing, you should, provably converge to this answer. The statistical part should hopefully allow you to escape these things and find the global solution, but at a much faster rate because you're leveraging the nice properties of the filter. So this is going to just be a quick run through of, the actual method in practice. So let's assume, I don't recall how many points I chose here, but, let's assume these points here that I've evaluated are from my initial Latin hypercube design. And so, the red points are the ones that are dominated, so they're not part of the filter. The green points define what my filter looks like. And so I already have some points that satisfy my constraint functions. So these guys who are at 0. And basically, this green value right now is my lowest value that I have found that satisfies the constraint. So right now, this is my current minimum. I want to iterate here. So I want to now see what's the next best point that I could choose. And so these blue points here are potential candidate points that I am going to predict at to see which one has the best, the best chance of being outside of the filter or being acceptable to the filter. And so the way we did it in the paper, it could be done several different ways, but these blue points are chosen as candidate points from a Latin hypercube design. Each one of these blue guys that I'm plotting here, this is where they would fall based on my prediction under the Gaussian process. And again, it's prediction, so there's uncertainty that's associated with it. And so you have all of these uncertainty ellipses associated with it. And you can see that the size of these ellipses vary. They vary based on where data is. So you can see up here, you have a handful of data points. And so predictions that are close to there may have small ellipses because they're close to data. Areas such as in this area where there's no data collected should have larger ellipses. And so that's a property of the Gaussian process, and it's an intuitive property, is that your uncertainty shrinks around points that you've observed, and your uncertainty is high in areas that you haven't observed yet. And so from here, after one update, we'll select a point that has the largest proportion of its ellipse outside of the filter. And this is now a picture after, say, I've ran my algorithm for 25 updates. And so I've selected 25 new candidate points. So you see in here, I have a bunch of green points that, these are the points that I've selected perhaps. And so I will iterate this algorithm, right? So every time these blue points are my predictions, I get new uncertainty ellipses. Down here, these little ellipses, they're very tiny little red circles because I have a lot of data here. And this is one of the nice things about leveraging the statistical properties, because with the filter method, you might get into these areas and get stuck just because you're kind of close to solutions. And so you might not explore some of these points that might have high uncertainty that could get you out of those areas. So you might think to yourself when you see this that you're only grabbing points that are down here, but some of these ellipses are going to grow large enough that they're going to fall past this, and we might end up selecting points in this area for a little bit. And as we learn about that area, we'll stop exploring it if it doesn't seem promising. This is it after 50 updates. And so you can see they've shrunk up here as we've gathered more data. They're continuing to shrink. And this is after only 50 updates. This is, what my space looks like. This is what the true filter looks like. So all of these red points are dominated points. All of these green points are the guys that define the boundary of the filter. And you can see, you see right away that they look very similar to one another. So we're capturing the actual trend of the true filter very well. And here is the best objective function that satisfied the constraint in this example case, right? So it's negative 0.86718, and the true solution to the problem is negative, it's the exact same answer. And so after only 50 updates, we were able to find the true answer in a problem that, if you thought about this as like the real world application of it, a very expensive function, we only had to run that expensive black box 50 times, which might have been a very long process anyway to do. Here are some results from the actual paper. And so we looked at a problem that was introduced in this Gramercy et al. Paper, 2016. You have a linear objective in two variables. So this is the function. So this is a toy example. It's not a real computer model. But you have, this objective function, which is just a linear function of x1 and x2. And you have two highly nonlinear constraints that are given by these two forms. In their paper, they treat x1 plus x2 as known. But this is, even if you know the objective function that you're trying to minimize, I just want to make this point. Anytime you have some of these guys being black boxes, so if you have these highly nonlinear constraints that are black boxes, this can still be a very hard problem to solve, even when your objective function is known. I believe in our paper we treated even the objective function, even though this is typically, they wrote it as being known. I think we treated it as being unknown when we solved this problem. Here's a picture to give you an idea of what that actual surface looks like. And so the colorful area is the region of the objective function that meets the constraint. The grayed out area is what I'm calling the infeasible region. So this is where the constraint would not be satisfied. And so the minimum value is this green circle here that falls along the edge of the constraint space. And there's one global solution and there are two local solutions. So there's a blue little diamond here and a red triangle here. They're kind of hard to see, but basically you have three minimums that you could find. Two are local, one is global. You don't want to get stuck in these ones and you want to find this global guy. We had this note that's, constraint 2 may seem uninteresting. So constraint 2 defines this region up here. But it reminds us that solutions may not exist on every boundary, right? So this solution only exists on one of the boundaries of the constraint space. but you have this other part that kind of cuts off your space up there. So this is the results from the paper. In the left-hand side is the results from the Gramercy et al. Paper. They ran a battery of methods from the mathematical literature. So these are non-statistical based. I guess one of them is asymmetric entropy is a statistical based method, but the other ones are not. And then these methods here were the ones that they introduced. But just to give you an idea here, so their black methods are doing much better than the methods that existed at the time. And then in our picture here, this is the solution that we found. So this, and sorry, I should back up. Each one of these lines is if you were to, is the average solution solving this problem multiple times. So they start with an initial set of data, just like us. We would start with an initial set, run our algorithm, we get a solution. We then start with a new initial set, run our algorithm, get an answer, and we would do this over and over again just to see kind of how robust our solution is. And so in this plot, these are the average solutions found. So on average, they're doing much better than the other algorithms at finding the true solution. So I think I wrote it here. The true solution is 0.5998. So, down here at 0.6. So they're finding it. Our statistical filter algorithm, we're doing the same type of experiment here. We're repeating our algorithm multiple times and taking an average solution. So this dark blue line is our average solution. And so we ended up finding the same answer. We end up converging to the same answer at the end, the correct answer, but we do it in slightly less time through this region. Our method is a little bit quicker than the Gramercy paper that we were benchmarking against at the time. The shaded area is just to give you an idea of kind of the distribution of our solutions here. So this is kind of like the quantiles of our solutions to get an idea of where it all lives. Okay, so these were everything I've shown you so far has been on kind of toy examples. This is that Lockwood problem we're going to return to, right? So I had said, that they constructed a computer model to represent that physical system of, installing the pumps, turning them on, and seeing if anything, escapes in any contaminants escape into the Yellowstone River, while they're trying to minimize the cost of running the pumps while making sure that this constraint of the contamination status is always satisfied, right? So pumping rates are the things. So there's 6 pumps that we can pump. There's 6 rates that we can change, 1 per pump. There were 6 pumps. We're gonna explore the different pumping rates that are going to minimize the cost while making sure that we never contaminate the river. These are the results. So again, we benchmarked them to the results that were in the Gramercy et al. Paper. So it's the exact same type of plot. These dark black solutions are the better solutions that were found in the Gramercy paper. And so again, the Gramercy paper did a very good job of, beating out a lot of these other methods. And these these light gray ones were a paper that they benchmarked to. So this is original paper. This is their methods that they tested in their paper. Their methods do much better or, just as well as theirs. And so this is, again, the same plot where we're showing our average solution. And again, we do slightly better in the very beginning where we're, finding a lower objective value much faster. And then towards the end, we all kind of converge to the same area where we actually on average found a slightly lower answer to that than their answer. And so this is, the real world application of this problem on a real problem that we solved that it seemed to work well, our methodology. And so I'm going to conclude here. There was another example in our paper. I didn't want to put it into this talk, but there's one more real world example that was in there that you can read more about. But basically, the basic conclusions were that the filter approach, it provides provable convergence, which is why we chose to use the filter method. And the statistical surrogate modeling, it improves the efficiency of the filter method. So again, taking a method that's kind of has very nice local properties and taking a statistical method that has nice global properties, the marriage of the two, you kind of benefit in a sense from both of those types of properties. Multivariate modeling can improve surrogate modeling. I don't actually at this point anymore recommend it. Maybe I've just gotten lazy as I've got out of academia, but the computational overhead of modeling things using a multivariate Gaussian process, I don't recommend. It is cumbersome. the calculations. It's a lot harder than just fitting. And, the other thing is, most of us nowadays, you might use a package to fit these things. I don't think I've seen any multivariate Gaussian process packages or any that I would recommend, let's say. But there are lots of just regular independent Gaussian process type modeling packages that exist. And, we combine the two, obviously, for efficient constrained black box optimization. And that is the end of the talk. So thank you for listening. I know when I watch a lot of webinars, so if you've been following all of these FTC webinars, you start to get a lot of this, Zoom fatigue. And so thank you for coming today and listening to this talk. I really appreciate it. And yeah, I'd be happy to answer any questions that you guys might have.
Great, thanks so much, Tony, for a really interesting talk. So if anybody has any questions, feel free to type them into the Q&A box. We can give you a chance to do that. But maybe I'll start off with the question that I had as well, Tony. So I like the idea, because these black box models can be, very expensive to run, and you talk about how quickly your approach can converge to, say, the optimal solution. But I mean, those runs still do cost something. So do you have any recommendations of knowing, well, when can I cut off and say, well, here's the solution that I have to run with, because I either can't afford to do any more of the black box modeling computations, or is there some sort of recommendation of like, well, I'm close enough and I can call it a day?
Yeah, so it's funny that you asked that question. I'm working on a paper right now, basically kind of critiquing and slamming everything I've done up to this point, because I think there's a ton of papers out there that propose all these very novel methods. So this whole area, at the time when I wrote this, I didn't know that it was called Bayesian optimization, but this whole idea of like minimizing or optimizing black box functions with no gradient information, it's called Bayesian optimization. There's a whole slew of literature on Bayesian optimization. And I think there's a lot of really cool things that are out there, but nobody works on these very practical problems of like, how do I know I've converged? How do I know, what's my initial design for actually picking points? There's a lot of really simple questions that I think kind of get swept under the rug. For us, it was just, run it to budget, and budget for me is, how much computational power do I have on my computer that I can get an answer in a reasonable time. In the examples in the paper, it's easy because they're made up, so I can actually tell when I've actually converged to a solution. For the Lockwood problem, I just ran it until I had the same budget as the other paper, so I'm benchmarking against their numbers. From what I know in practice, it's really just a matter of budget. How long, if it takes you a day to get an output, is it worth trying to get 20 outputs that take 20 days? Or, does your project, is it so high priority that you're allowed to run it for 1 year? Is it, it's one of these questions of, what is the question that you're answering? And so there's not really, as far as I have seen, there's no actual methodology out there that, like some sort of epsilon method where you're saying, if I take this value and I take this value and they're within epsilon, I know I've converged. I don't think those exist yet.
Oh, thank you. Are there any other questions or comments from our attendees? Right. If not, Tony, thank you again so much for speaking with us today, and congratulations to you and your co-author on winning this award. And thanks everyone for being here. If you want to catch any of the webinars that we've had in the past, again, visit the FTC conference website, and we hope to see you in 2022. Thanks everyone, and have a great day.
Yeah, thank you guys.